Welcome back. Let's talk about neural nets. Here's the agenda. Biology, we'll look at a model, talk about training, look at some code, talk about the homework, and then work some examples. So what are neural nets? Neural nets are a computational method for simulating biological neural networks, also known as brains. Okay, so here's a brain. Let's say you got a brain. If you look at the cortex, that is the first few layers of cells, they call the cortex, which is I think just Latin or maybe probably Latin, not exactly sure, for skin. It's the skin of the brain. So there's like some layers of neurons, okay? And if you sort of blow that up, then what you see is like a neuron, another neuron, another neuron, a bunch of neurons, and they send these dendrites down to the next layer of neurons, like that. And then there's a synapse in here, okay? So they're sending a signal down their dendrite through the synapse to the next neuron, and that kind of continues down to the, first like 6 layers or so, approximately 6 layers, something like that. There's not a lot of layers. That's what's interesting, is that these brains do so much with it surprised me anyway, but there's only about 6 layers. Okay, so we can build a model, we can build a computational model whereby in each neuron we have 3 values. We have a threshold, and we have something called the effective weight, and then we have a Boolean called fire. So let's define these. So the effective weight is the sum of all the stimulation to that node or neuron. We're using nodes to model biological neurons. Okay, so the effective weight is the sum of all the stimulation coming down from the layers above. Okay, the threshold is the weight, or the weight above which this neuron will fire. Okay, and fire means that it's sending signals down to the next layer. Okay, so each neuron, it may or may not fire. That's this Boolean. This is a Boolean. The effective weight is a sum of all the stimulation that's coming down, and the threshold it's a comparison. It's a value we're using to compare. All right, so that's the basic idea. Now these things need to be trained, and the training basically consists of adjusting. So training is adjusting. We're adjusting the threshold values, right? We're adjusting how sensitive the entire neuron is to firing. That's the threshold value. Okay, and then we're adjusting the synapse weights, or you could call them the link weights. That's training. So we can adjust basically whether each neuron fires, right? That's this Boolean, whether this neuron fires at all, right? And then if it does fire, how much does it fire? Like how much are these synapse weights in here? Like how strong is it stimulating the next layer? Okay, and that's how these things are trained at the simplest level. And the training, we call that learning, right? So when you, as a human, it's a biological entity, when you learn something, you're training your neural net by adjusting the threshold of the neural net and the strength of the stimulations down to the next layer. This is a very simple model of what's happening in biology. It gets very sophisticated. And I do want to say, this is a first semester data structures class, so my goal here is to just introduce you to the basics of neural net. You could get a PhD in neural net stuff. It's there's a lot to it, and the training algorithms are pretty sophisticated. But like I say, I just want to expose you to the basic idea of a neural net because it's so important. It's becoming increasingly important. There's a lot of neural net computations out there. Okay, so let's see. I have some code that simulates this, and then I'll work some homework and examples. But we can work on the model a little bit more. So let's say let's just look at a two node layer. So there's one layer, and here's another layer. Just that. So this guy's going to come down with a link weight. And then another link weight. Let's give it a weight of 1 and then a weight of 2. Okay, then this guy's going to come down and stimulate its next layer, and let's give this a weight of 3 and this a weight of 4. So let's say the sum here of this, it's getting stimulated. The first row stimulation is just the input. So let's give it a value of 42. So let's say the input is 42. So we'll put a 4 in here and a 2 in here. Okay, the sum is 4 and the sum is 2 on this guy, on the first node. So this guy's getting an input of 4 and this guy's getting an input of 2. Let's give it some threshold values. Let's give a threshold value of 2 and one of 4. Okay, so this one's getting stimulated more than its threshold, so it will fire. So the Boolean will be 1. This one getting stimulated less than its threshold, so it will not fire. Okay, so once again we have the effective weight, which is the sum of all the stimulation from the layer above. We have the threshold, that is the value above which the neuron will fire. And then we have the firing Boolean, which is, well, the result of comparing these two numbers right here. Okay, so 4 is, so basically just to be totally a little more. So this is 4 greater than 2 gives you a 1. This guy here, 2 is less than 4. This Boolean is just a comparison of the amount of stimulation, also called the effective weight, compared to the threshold value. Okay, so this neuron's is going to fire, and this neuron will not fire. So this guy's firing. He's sending a 1 down to this node, and he's sending a 2 down to this one. So this one, the sum on this one is going to be 1 plus 0. Really, it's just going to be 1 because it's 1 times 1 because it's getting a stimulation value of 1, and this one's firing, so you could write that as 1 times 1. This node here is sending a stimulation value of 3, but it's not firing. So you could write that as 3 times 0 if you were, in the calculation that happens in the software. That's what you do. So this is 1. That's where that 1 comes from. This one is going to be, it's going to be a link weight of 2, which is being sent. So you just multiply times this Boolean, right? 2 times 1 plus 4 times 0, which is just 2. So this guy gets a stimulation value of 2, right? Then it's going to have some threshold values that you put in, or some threshold values that you put in there. Like let's put in a 0 and a 3. So this one will fire, and this one will not fire because this one will fire because it's being stimulated at a value of 1 and the threshold is 0. So the effective weight is greater than the threshold, it'll fire. And this one here, the effective weight is less than the threshold, so it will not fire. And it just kind of continues on down like that through all the layers. That's how these things work. And my goal is to get you familiar with this calculation process. Okay? And once you understand that, then you can start thinking about more, the training and architectural issues and all these other things. Before I move on, so this makes up a functional unit. And this, or FU. And there could be another FU over here and another FU over here. And this little FU will have an output, and it might come into this guy, and then this guy, it'll trickle through this part of these neurons, and then it'll maybe come over here, and it'll trickle through these guys. And it's very interesting. Like if you study this, like you might have an eyeball, and eyeballs they do some processing close, and then they send a bunch of stuff to all these functional units back here, and then they send them over here, and then then they send it over here. It's very interesting. A lot of this stuff happens subconsciously, a lot of this pre-processing in the brain. Anyway, it's a very interesting subject. Okay, so this is the basic biology, and then from this basic biology of neurons, we ended up with this model, which sort of simulates what nature does. And the training comes down to setting the link weights and these threshold values. Okay, now I have some code. So that you could download this, right? So I've modeled this guy right here. I've modeled this thing with this here it is. This is the net. It's called net. This guy's a 4x4 net. So there's four nodes on a layer. Well, this is a 2x2 here, but in this code, it's 4x4. There's 4 across this way and then 4 deep. And it's just in a 4x4 array of nodes, and or an n by m array of nodes. And then each node has this stuff inside it. It has the threshold, right? It has the threshold value, the effective weight, and the Boolean on whether it's going to fire. Okay, and then these links coming down, that's an array inside of the node, right? Because this node has these 2 links coming down. And if it were a 4x4, it would have 4 links. So it's an n, the number of nodes per layer, and link weights. So that's a net. That's this net if it were 4x4. All right, so when a baby is born, it doesn't know anything. Well, I mean, it knows very little. And you could think of that as an untrained neural net. So I have this init function here. All it's doing is running through the 4x4 array and setting all of these threshold values to just some arbitrary number. 10 is totally arbitrary. And I go through that. And then I think I set the link weight. Yeah, weights. So that gets pretty big, right? Because this is one node, one node, one node, one node. And then for each node, actually one layer of 4 nodes, and one layer of 4 nodes, and one layer of 4 nodes. And then each one of these nodes has 4 links. So this is layer 0, the 4 links on layer 1, on layer 1. It's the 4 links coming out of this thing, and this is the next 4 links coming out of the next node, and the next 4 links coming out of the next node, the next 4 links coming out of the next node. So these 4 paragraphs here are the link weights for layer 1. Okay, it's pretty mechanical here, but the thing is, the threshold values and the link weights are all 0, or they're arbitrary. I just used 10. Totally arbitrary, and then I used 1 for the link weights all the way down. It's totally arbitrary. Anyway, this builds a neural net that looks like, well, to be totally abundantly clear, builds an m by n neural net where m and n are both 4, and these are all ones on the these are all ones on there, and then the thresholds are all tens. So it's just builds this guy. So we need to train it, okay? But I'm going to ask you guys to train this manually by going through and just setting these values, hard coding. Just type a new value in here and then recompile. Hard-coded training. Hard-coded training. Right? That's the goal of this thing, is just to get familiar with this processing. So what else do I got in here? I have the PrintNet just prints out the neural network. Just prints out these values in here, and then I have this calculation, because these guys fire and they send signals down, and then you got to sum up, and then you got to calculate whether it's going to fire again, and then sum up and calculate whether it's going to fire. That's what's happening here. You can go through this code if you want. It's understandable. You don't absolutely need to totally memorize this or whatever, but it's there should you need to understand these calculations a little bit better, which you kind of do. But here, I'll get to what I'm asking you to do. And then this is the main that's just reading words from an input file and running them through the neural net. So look, maybe we'll come back to this, but look, what's the homework? The homework? I'm asking you to take this code that I've already written for you and get it to work for these two input sets. So there's a set of woody words called wood, gone, food, hoop, and spam. All of those words are in the category of woody. And then there's these four words here: tinny, meep, beak, pawn, and meat. And those words are all tinny. So I want your neural net to determine whether a word is woody or tinny. That is, I want you to train it on these two sets. So you're going to train it on this set of woody words, and it should identify them all as woody. And then you're going to train it on this set of tinny words, kind of at the same time. You train both of these. You'll train it on this input set, and it should identify all these input sets, all of these words in this input set as tinny. Okay? So you're basically teaching it what woody words are and tinny words are by hard coding the link weights and threshold values. Okay? So you'll get it trained. Then you'll send it out into the world and give it a job. And its job is to find new words and tell you if they're woody or tinny. Okay? So then you'll feed in a new word, like any four-letter word, like what's a four-letter word? Spam's in there. I can't think of any. I can't think of a four-letter word right now. Link. There's one. L-I-N-K. Feed that in, and the neural net will tell you whether it's woody or tinny. Okay, now keep in mind, woody and tinny are just totally made up categories. There's no such thing in real life as woody or tinny. The point is, you're going to train it on these words and then give it new words, and it'll tell you whether those new words, which category they fall into. Okay, so that's the first part, the implementation. I want you to modify the source code to recognize woody and tinny words. And then I want you to draw that diagram out on what it looks like for the word food. I want to see what the manual calculation looks like for the word food. And then I want you to give me some estimates for the time and space complexity. Maybe we'll come back to that. Let's look at some calculations. So here's a simple, let's do this one first. So this is posted. So this is a cat finder. It finds cats. It's been trained to find cats. Because that's what neural nets do. You train them. It's just like, in people, the same thing. Like a little kid, there's cats and dogs walking around, and he points at, the cat and says, "What's that?" And mom says, "Cat," And then he points at another cat, and mom says, "Cat." And after looking at about, 5 or 10 cats, he knows what a cat looks like. He's trained. And the same thing with dogs. He looks at dogs, and mom tells them, you know, it's a dog, and then so there's an input set of cats and an input set of dogs that the neural net gets trained on. And then after that, it can recognize any cat or any dog. That's what we're trying to do. We're going to train it on woody words and tinny words. And then after that, it'll know, it'll be able to give you an answer for any new word and tell you whether it's woody or tinny. But this guy is just doing cats. So we have our threshold, we have our effective weight, and then we have fire. Once again, the weight is just the sum of all the stimulation coming into that node. The threshold is the weight value above which the neuron will fire. And fire is a Boolean 0 or 1 indicating whether this thing's going to fire. It's just the result. Fire is just the result of comparing weight and threshold. So here I'm feeding cat in using the index of the letter. So A is 0 and Z is 25. That means C would be 2. Right? If you just start numbering letters from 0 to 25. And then T happens to work out to be 19. So I'm feeding in 2, 0, and 19 here. So there's 2, there's 0, there's 19. And then I came up with these threshold values, 5, 10, and 15. So this node here, the effective weight is less than the threshold, so the Boolean fire is 0. So this node will not fire. This node here, same thing, this will not fire. This one will fire because the effective weight 19 is greater than 15. Okay, so no fire, no fire, fire. So this guy is sending values of 7, 8, and 9 down to the next layer. The other two aren't doing anything because they're not firing. There's link weights on here, but they're not being used for these first two nodes because they're not firing. But this one is. It's sending a 7 down, so that's why you get a 7 here, because it's getting this 7. It's getting a 0 from this node, and it's getting a 0 from the next node. It should be a 7. Should be a 7. Oh, it's posted with this typo in there. Shoot. Anyway, this should be a 7 because this one's firing and sending a 7 down, so that's where the 7 comes from. And this one, likewise, it's getting the 8 from this node, and it's getting this guy's getting a 9 on this link from this node. And then I have some other arbitrary threshold values. So this one, 7 is greater than 5, so it fires. 8 is greater than 5, so it fires. Here, 9 is not greater than 10, so it does not fire. So this 1, 2, and 3 do not come down because this guy's not firing. But the 4, 5, and 6 come down because this guy's firing, and the 7, 8, and 9 come down because this guy's firing. So this one, it's getting the 9. This 15 here, it's getting the 9 from this guy who's firing because the link weight is 9, and this guy's firing. It's getting 6 from this node because this node is firing, and its link weight is 6 on this link. This guy is not firing, so the 3 is not coming down, so I just have a 0 here because this guy's not firing. So it's 9 plus 6 is 15. Okay? And then I set up some more threshold values, a 10, a 15, and a 10. So 15 is greater than 10, I get a 1. 13 is less than 15, I get a 0. 11 is greater than 10, so I get a 1. And the final value is just the value on the bottom row here. It's 1, 0, 1. Okay, so the final value of the fire booleans on the last row is 101, and the criterion I set was anything greater than 3 binary is a cat. So basically looking for a 1 right here. Or you could specifically look for 101 or decimal 5. I mean, whatever you want, but you look at the last booleans here, and you come up with some criteria to identify. Like for woody and tinny, I suggest you use any value greater than 7, because basically you'd be looking for a 1 here on a 4-digit binary number. If there were 4 nodes here, you'd be looking for a 1. Okay, so the point of this example here is just to show you the calculation process for an arbitrary set of numbers. Cat is just kind of arbitrary, and these threshold values were arbitrary, and the link values were arbitrary. I just want to show you how the calculations work. Okay, but what you're really trying to do is identify categories, right? You're trying to identify cats and dogs, or Woody and Tinny. That's what neural nets, at the simplest level, that's what they do, is they categorize things at the simplest level. So here's another example showing categorization. Okay, so this is East Coast versus West Coast. So here's a calculation using an East Coast state, and then a calculation using a West Coast state. I did California and New York. So here's some West Coast states. I got California, Nevada, Oregon, Washington, and then here's some East Coast states. I got New York, Florida, Connecticut, New Jersey. And then I numbered the letters 0 to 25. So I'm trying to encode the input so that I need numbers to put into this thing. So California becomes 20 because C is 2 and A is 0. Okay, Nevada becomes 1321, like that. New York is NY, which is 1324. 1324. All right. So let's do the calculation for California. So California, CA would be 2 and 0. So that's the first weights that get fed in, just the input data, 2 and 0. So then I set some threshold values. This thing works. It works for California and New York. I actually haven't tried it for the other states. But the idea is you would adjust it until it works for all. It correctly works for all West Coast and correctly works for all East Coast. And then you'd feed in some other state and it would tell you which group it's in. Like you could feed in Nebraska, what is Nebraska? NB? I don't know. You'd feed that in and it would tell you whether it's East Coast or West Coast. Or Texas. I'd say Texas I'd call it West. But that's just me. But the idea is you train it on a training set to get it to work consistently for these states and these states. Then you'd feed in new states and it would give you an answer. That's what humans do. We learn on an input set and then we go out in the world and we apply that to new data. We identify new cats and new dogs. Okay, look, back to the thing. So I feed in the 2 and I feed in the 0, and then the link weights. The link weights I used a 10 and a minus 10. Same down here, 10 and a minus 10, and then a 10 and then a 10, 10. Okay, so I use this. You have to use the same link weights to get it to work for all of this, both sets. Then I set these threshold values. I used a 1 here and a 1 here, and a 1 here and a 1 here and a 1 here. And likewise down here, same thing, 1, 1, 1, 1, 1. And what happens when you feed it California? The 2 is greater than 1, so this guy fires. It sends its 10 down. This guy here, A is not greater than 1. So it does not fire. So this minus 10 does not go down. So the effective weight on the next layer down is just 10. It's 10 times 1, or 10 times the Boolean, plus minus 10 times 0, which is 10. Basically just the 10 comes down, this one 10. And then you just continue like that. So this guy has a higher effective weight than the threshold, so it'll fire and send a 10 down. And this guy has a higher weight than the threshold, and it sends a 10 down. Anyway, you get a 1 down here, and then that's binary 2, which is West. So I set it up. West is identified by the values on the last row, either a binary 2 or a binary 3. And then East Coast is identified by the two fire booleans at the bottom. 0, 0 is east, or 0, 1. So basically, you could look at the bottom row as a binary number. Any value bigger than binary 2 is East Coast. You could do it that way. Okay, so this works for California and New York. Correctly identifies California and New York. I don't want to make it too complicated, but you'd have to set up threshold values and link weights to get it to work for all of these guys consistently. That's the problem. So you need to look for patterns. So like here I'm looking, like I think I'm looking for the first letter, like CA, NV, Oregon, Washington. Let's see, that's not, let's see, AVRAYLTJ. You might be able to find some patterns in here where these guys are consistently bigger than these guys. That might work. Or you might be able to, you could find the first couple digits on this side, and then you could find the next couple digits on this side, right? That is, you could look for N's and W's over here, and then you could look for F and C over here, or something like that. Okay, so I want you to play with it, and because playing with it makes you really think about how it works. I don't want to give you too many hints, because I really want you to play with it. That's what you need to do for this introductory part of this thing. And then later on in life, when you transfer something, you could take a course just in neural net training, and you'd be ready for it. Okay, you'd be ready for all the algorithms. Right. Let me show you another example on closer to the homework. Okay, now the homework. This thing, I want you to use this training set. Get it to consistently identify these 4 words as Woody, then get it to consistently identify these 4 words as Tinny. And once you get it trained, try some new words and see what happens. So I showed you a calculation here for my solution. Is this my solution? I think this is a partial solution. Yeah, this is a partial solution. Why am I showing you this thing? I hope this isn't the real solution. I don't know. Maybe you're getting to get lucky, but I doubt it. Okay, so I'm feeding in wood. W is 22, O is 14, O is 14, D is 3. So the 22, 14, 14, 33, that's just wood. And then I came up with these threshold values, 10, 13, 12, and 4. And then I came up, for the first node, I came up with these link weights, right? For this node is first link weights. And then this node has these link weights, and then this one has this link weights. Here I'm using a -10 link weight. And then you just crunch it through, and it comes out to Woody. And let's see. So let's see, 22 is bigger than 10, so this guy fires. 14 is bigger than 13, this guy fires. 14 is bigger than 12, this guy fires. 3 is not bigger than 4, so this guy does not fire. So basically the first 3 nodes are firing, so they're down here. The link weights will come through for this sum. This one it'll be 1, it's 21. It's 1 plus 10 plus 10. Gives you 21, because this guy's not firing. This guy, 1 plus 1 plus 1 is 3. This guy, it's 15. So I got fire, no fire, no fire, no fire. So I'm just going to get this 15 from the first node that's firing. And in the end, I end up with a 1000, which I'm interpreting as a binary number. And it's greater than 7. It's 1000 is 8 binary, or 8. Well, it's 100 binary. It's 8 decimal, which is greater than 7, and I'm counting anything greater than 7 as being Woody. All right, so what you got to do here? You got to take this thing get it to work. Should work, straight out work, barring any syntactical trivialities on your environment. Get it to work. And this is just a newborn baby. It doesn't know anything about Woody and Tinny. And then I want you to get in here and teach it stuff. Get in here and adjust these values so that it's consistently identifying Woody and Tinny. How? You know, a little bit of guessing, a little bit of insight, a little bit of randomness. You know, make some changes, see what happens. Yeah, that's part one. I want you to just train this guy manually and get it to work. Then feed it some new words. Okay, then do a diagram. Basically, what I did here for cat, draw that. Draw that. That's part 2. Draw that for food. Draw something similar to this, but just for food with your numbers. Okay, with your link values that you came up with. Okay, let's talk about time complexity and space complexity a little bit. Neural net, time and space. Okay, look, if you have all of these guys, what about time? Well, if you're simulating this on your PC basically has one processor. I mean, maybe you spent a lot of money and you bought a 32 core machine, so it has 32 processors. But compared to the number of nodes, it basically has one. You know, I mean, if you had 1,000 nodes, I mean, you basically have one processor. You basically have to, it's not exactly true, but I'm saying the comparison, right, between how many nodes and how many processors you have. So what would be the time? It would be, you would have to wait for this summation to happen, then this one, then this one, then this one. You'd have to sum up all the link weights. Well, the first node isn't summing any, the first row isn't summing anything, but every row after that, you'd have to sum everything, right? Then you'd have to do basically what I'm saying, you have to do a serial sum and compare, you know, for each n. It's basically going to be a big O of n kind of a thing, where n is the number of nodes. It takes a long time. And how many neurons do you have in your brain? I hope a whole lot. I hope it's on the order of billions. Right? So if you're using a serial calculation on billions of nodes, it's going to take a long time. Because each node, you have to process for each node, and there's billions of them, and then each node has to do a summation of the entire row ahead of before it, right? And then it has to do the threshold weight and effective weight calculation. It's a lot. It's going to be, you know, minimum big O of n. It's probably going to be worse than that if you're doing it serially. That's kind of the time thing. So what we really need is a parallel. So there's serial, then there's parallel. Just thinking about the computation part. Because remember, there's there's the computation part. Okay, so basically what I'm getting at is that your computer is a serial machine. You know, your PC, whatever you use to get your homework done, it's basically a serial machine in comparison to the number of nodes here. But what we really need is a parallel machine, kind of like your graphics coprocessor, if you have one of those. Those things are highly parallelized because these summations can be happening at the same time, right? So basically, you'd have a computing device, you know, for each node, and that's what's done, you know, in practice. because you don't want to wait for each one of these calculations to happen. You want them all to be going at the same time. For each layer, you want a processor for each one of these nodes, so that all that layer can be calculating all at the same time. You still have to wait for that layer to finish before you can go to the next layer. But like I was saying at the beginning of this lecture, there's only about 6 layers. Okay, so that's what I'm talking about in time complexity. Is what if you had a serial machine? How long would that take? Okay, so that's what I'm asking here in part 3, time. Calculate a time estimate. Assume a serial calculation with this big O. I want you to come up with some actual time for this calculation right here, and then work that out in actual seconds for how long this would take. Do that. Okay, then what about space? So this was time. You know, talking about a little bit about serial computation versus parallel computation. It's still time. There's one other thing that happens with neural networks, and it's just the wires. So as n increases, let's call as this increases, the number of wires increases at the square of that. Right? There's n squared wires. Okay? So, you know, as you add more nodes, you have to add that many wires, right? If I add one more node on here, on this layer, I have to add that many wires down to every, right? Add one more node, add a bunch more wires. So this, basically the idea is that wires are the limiting factor in n. And it's the same in your brain. Back here we have these functional units. The layers are only so long. It's because of the synapses. They just take up too much room. So your brain has solved this problem by coming up with these little functional units. Okay, that's the space complexity. So here I'm asking you to think about the space and come up with an estimate of how big each one of these units would be. Okay, what am I asking for here overall? I just want you to get familiar with neural nets. I want you to think about neural nets. So I want you to just get this thing to work as best you can. That'll help you understand how they do the processing, and the diagram will help you do that. The time and space thing, you know, there's no perfect answer on this, but these 2 questions are designed to just make you think about these things, to get your biological neural network primed with this idea of neural nets, so that in the future, if you have an opportunity to study these more, you'll be that much more ready for it. Okay? That's it. Have fun.